Hey everyone, welcome back to the channel. Today we're going to be looking at equilibrium and the K constant. So let's just dive right in. Okay, so probably in class up until this point, you've only seen reactions with a one-way arrow, right? A reactant with a one-way arrow that forms a product. And this is a reaction that goes to completion. But at this point in your learning, maybe you're starting to see this double-sided arrow that I have here. And this indicates a reversible reaction. And this indicates a reversible reaction between a reactant and product that can also be an equilibrium process. So I'll get into that in a second. But this is going to be sort of our general expression of an equilibrium process. Reactant A, that is in a sort of reversible mechanism with the product B. And so we can define this equilibrium as when the concentrations of the reactant and the concentration of the product does not change with time, or seemingly doesn't change with time. So I'll explain that sort of definition in a second. It'll make sense. But I just want to have a little bit of a visualization for everyone here. Let's just look at this graph. So we're going to assign some of these curves. So this black curve, we're going to assign it as the reactant A, the concentration of our reactant. And the red curve will be the concentration of our product B. So let's start from the beginning of a reaction, right? Let's say we have reactant A and we do not have any product yet, okay? This is the very beginning of a reaction. So we have a certain amount of concentration of our reactant A, and we're going to start to form B. And as we form B, we must use up A, right? That's how the reaction normally goes. So that means that our concentration of A with time is going to start to decrease as we form B. And when we form B, our red line here, as we're increasing our concentration of B because we are forming it, because that is the product, we are, decreasing A and we're forming B. And there comes a point where they both sort of plateau here. And this is, this time point here, this period here is called our equilibrium. There's a point in time where we are in equilibrium where the rate or the speed at which we form B equals the rate or speed at which we react or use up A. So it's important to note that this doesn't mean that the reaction ends per se. We're in something called a dynamic equilibrium. So A is reacting to form B, and we can actually do the reverse process because this is a reversible reaction. B can react to form A, right? So like I said, the rate of the forward reaction in equilibrium is going to be equal to the rate of the reverse reaction. So that definition that I gave you a little bit earlier, where the concentrations don't seem to change with time. So what I mean by that is we have our reactant, we form product, and we can do the reverse as well, form reactant. And let's say, for understanding's sake, we do this, a bunch of times. A forms B, B goes back to form A. A forms B, B goes back to form A. Back and forth, back and forth. Well, if we're going back and forth so quickly, so often, so much, it's almost as if the reactant A, the concentration of this, it's almost as if it didn't change, right? Because as soon as we, form B, we form A again. And this is, assuming we fully form A again after we've used it all up. There's some assumptions you're making here, but this is sort of the idea here. We're going back and forth, and it's as if the concentrations sort of stayed the same because the rates of the forward equals to the rate of the reverse. So we're just able to go back and forth, and this is our equilibrium process. And this is like a perfect ideal equilibrium sense, if you will, for this, theoretical example that I'm giving you. Now, so what we have here on the left side is a couple examples of two types of equilibrium that you might see in class. We have physical equilibrium as well as chemical equilibrium. So physical equilibrium, which is up here, this is where we have a phase change between a single substance. In this case, it's our bromine, so we're going from liquid to gas. And so physical phase change, that's kind of how I remember it. Now, if we look here in this bottom example, this is a chemical equilibrium example where we have two or more substances that are in the mix now and we form a product. And so this is not a phase change, this is basically a chemical reaction, if you will, that is in equilibrium. Okay, so we have our expression here that we've sort of set up in just earlier there. We have our reactant A that is in equilibrium with our product B, and they're in a reversible reaction here. And so we said that the rate of the forward reaction, when we're in an equilibrium process, the rate of the forward reaction equals to the rate of the reverse, and this is how they are in equilibrium with each other. And so how does that relate to this value K, this K constant, the equilibrium constant? Well, we can write out what I just said earlier. We can write this out in a little bit more of a scientific expression here. We can write the rate, the K value, the rate of the forward reaction of our concentration of A equals to the rate of the reverse reaction with our concentration of our product B. And so here, when you see square brackets, that tells us concentration. So whenever you see in class, if your teacher ever has something written in square brackets, that is indicating that it is a concentration of something, and we'll get into that a little bit later. But this is our general setup here that we have. Now we can actually, create an expression here with the rates on one side and the concentrations on another side. So, if we start isolating, dividing, as we can see, we have the forward over the reverse reaction equals to the concentration of B over the concentration of A. And so I want you to pay close attention here. It's not just arbitrary concentration of B over concentration of A. It's very specific. It's concentration B, aka the product, on the numerator, and then concentration of A, the reactant, as the denominator here, okay? So that's something that you really want to pay attention to, because this setup, this expression here, is equal to our KEQ, our equilibrium constant. So our K constant that is at equilibrium. So this is the general formula, if you will, that you should probably be very familiar with in class in order to do well in this section. So you have KEQ, so the equilibrium constant, equals to the concentration of your products over the concentration of your reactants. So this can be anything. In this case, I just have it as B because we're following my little general example that I have here, the B over A, but it's really products over reactants. So that's what we want to remember. Now here, keep in mind, I have it written as concentration, but it's not always concentration, and we will see that a little bit later in this video, but always remember products over reactants. That is how we find KEQ. And this is in the simplest form that a question can be. You could get values of concentrations, for example, of your reactant and your product. And let's say you were asked to find KEQ. You can sort of plug them in, products over reactant, and that's how you would find your KEQ. That is sort of the simplest question stem that you can get. Obviously, it can get a little bit more complex with a little bit more, steps in between to find these values. But this is where it all boils down to. Products over reactants equals your KEQ. Okay. Right, so we have our KEQ is products over reactants. Okay, so let's talk about what it means to have, a high value for K or a low value for KEQ or some sort of intermediate value, if you will. So let's go through some of these scenarios. If we have a small value, a small K value, so if this KEQ, the equilibrium constant, is a small number, okay, what does that tell us? That tells us that we have a lot of reactant in our sort of system process that we're looking at. So we have a lot of reactants in that reaction. So how do we, for some of the people that are a little bit more math inclined, this might make a lot of sense because it's really just fractions that we're dealing with. But, sometimes it's a bit harder for you to visualize, so I can help you out with that right now. Let's visualize it like this. Let's say I give you a fraction 2/1, okay? Obviously, we know that 2/1 equals to 2. that 1 is, it's as if it's not there. It's sort of an invisible 1, and it equals to 2, right? This numerator is way higher than the denominator, okay? Well, not way high. It's one unit, one value higher, but it's, higher. It's bigger than the denominator, and that gives us a certain number for our answer, right? Let's do the reverse. Let's say we have 1 over 2. So 1 is our numerator, 2 is our denominator. Our denominator is a bigger number now, and notice how our answer is smaller compared to this answer. So 2 over 1 equals to 2, but 1 over 2 equals to 0.5. And so this is kind of the sort of logic that you want to apply to this. When we have a larger number on our denominator, this is a general math thing. When we have a larger number in the denominator, our value is going to be smaller. It's going to get smaller the larger this number gets. So when we have more reactants in a reaction, well, when we calculate our KEQ, reactants is always on the denominator. So if we have a higher amount of concentration, for example, of reactants, this number gets bigger. And so our KEQ, this value, is going to get smaller the higher this number gets, okay? So if this is 1 over 2, for example, let's say we have, the concentration of 2 molar reactants and 1 molar of product, then we get 0.5 as our KEQ, for example. This is all just a random example I'm pulling out for you. As opposed to if we had a concentration of 2 molar of products over 1 molar reactants, where we would have a KEQ value of 2. So I hope you can see that. And so that brings us to the next point here. What if we have a large K value? This number, this KEQ, was super big. Well, so it's the opposite of this, as per this little example that I have here. So if we have a large K value, that means we have a higher number for products. We have more product than we do reactant. Okay, so our numerator is a bigger number, and therefore our KEQ value will be a bigger number. So these two, in a sense, are sort of proportional in that sense. The higher this number gets, the higher this number gets. The higher this number gets, the smaller this number gets, right? So KEQ and the reactants are sort of inversely proportional, and KEQ and products are directly proportional, if you will. And this is sort of the numerical, if you need numbers to help you understand how these relationships work, those are sort of our examples there. Okay, so what if we have a K value that is some sort of intermediate value, okay? Normally we consider a small K value, I believe it's 10 to the negative 5 or smaller. A large one, I think it's about 10 to the 5 or 10 to the 10 if I'm not mistaken. I think it's 10 to the 5 or larger, so that would tell us a large K, because that's a very big number, 10 to the 5. So an intermediate K is anywhere in between 10 to the negative 5 and 10 to the positive 5. So that would tell us we have some form of intermediate K value. And what does that mean? So this is sort of K is in between two values. So sort of in between 10 to the negative 5 and 10 to the positive 5. I'm sure you're probably hearing these values in class. So hopefully this is putting that into context for you. So if you didn't understand why is my teacher saying 10 to the negative 5, 10 to the positive 5, it's just to tell you, it's sort of like a benchmark as to what is a small k versus what is considered a large K value versus if we're in between those two, we're considered intermediate, if you will. Okay, so let's say we're at the intermediate part. We're somewhere in between those two values. What does that tell us about how much product versus reactant that we have? Because when it's large K, we know we have a lot of product. When it's a small k, we know we have a lot of reactants compared to the products. When we're intermediate, that means we have both species that are present in significant amounts. So it's a bit harder to tell how much of what we have. So, that involves a little bit of math, and that'll show up in future videos and definitely in future lessons in your class as well, I'm sure. Okay, so let's go with this general reaction here. A plus B, so these are our reactants, are in equilibrium with C plus D, our products. And they all have some form of coefficient in the front, okay? A has some form of coefficient that we label, lowercase a, has lowercase b, c has a coefficient of lowercase c, and d lowercase d. So these coefficients can be any number, like it could be a 1, it could be a 2, it could be a 1 and a 3, this is just for the sake of generalizing things, okay? So we said that our KEQ value is products over reactants, and in the earlier part of this video, I talked about a concentration, okay? A concentration would indicate that we have a solute, or we have something that is dissolved, right, in aqueous. That's normally what we see here as the states. We usually will see aqueous, we'll see that in our reaction here, right? Telling us that it's dissolved. That tells us that we're going to talk about concentrations. That's where the question is going to go. That's where your teacher is going to give you a concentration in moles per liter, also known as molarity, molar. So you could see it written as a capital M for molar, or you could see it written as moles per liter. Right, so why is this a concentration again? Okay, I want you to think back to the formula for concentration, okay? What is that again? C equals N over V. I'm really hoping you remember this from high school, or if you're in high school, your previous year, if you're in grade 11, I'm hoping you remember some of your grade 11 math, some of your grade 11 Gen Chem, I should say. So concentration equals to moles over volume, right? C equals N over V. That is the general formula for concentration, and that's what we're talking about here. Moles over a volume. In this case, it's going to be liters. That's what it has to be. Moles over liters, and this equals to molar. So these are interchangeable. Your teacher or your professor, if you're in university, they could give you a capital M, or they could write it like this, moles per liter, but they are interchangeable. Okay, so how do we write our KEQ in that case? So let's say everything here is written as aqueous, the phases, aqueous, there's, in brackets, aqueous and aqueous. So we would write it this way. We would have our KEQ equals to the concentration, so in square brackets, concentration of our products over reactants. So our products are D and C, and they are going to be put to the power of, raised to the power of their coefficients. So D to the power of lowercase d, C to the power of lowercase c, whatever these numbers are. So they could be anything, which is why I kept it so general here. And then over products, concentration of, over reactants, concentration of reactant B to the power of B, concentration of reactant A to the power of A. So these are getting multiplied, and these values are getting multiplied. And then this fraction, so whatever this number is over this number, is going to give us our KEQ value. And this is if we are dealing with aqueous solutions, solutes, concentrations. Okay. If we are in the gas phase, if everything here is written as gas, for example, how do we write our KEQ expression? So we know it's still going to be products over reactants, but it's not concentration anymore because we're not given moles per liter. We're in the gas phase. So I really hope you remember some of your, ideal gas laws and things of that nature. PV equals nRT, a little bit of that. Partial pressure, if that rings a bell, I really hope that rings a bell for you, because that's what we're going to talk about here. So let's say everything here is written in the gas phase. So the subscript here should say gas. We are going to write it as products over reactants. So it's going to be the partial pressure of our products over the partial pressure of our reactants. That's how we're going to solve for KEQ in this case. Okay, so it's going to be partial pressure of our product D to the power of lowercase d times the partial pressure of C over the partial pressure of our reactants, and they're going to multiply by each other. And then this final answer, so whatever the numerator is divided by the denominator, is going to give us the KEQ. So that would be our answer. Okay. Let's talk about if we have a solid or a liquid. Okay. So if we have a solid, if anything here, if they're all written as solid, for example, or some of them are solid, or some of them are liquid, for example, they will not be included in the equilibrium expression. Okay, so why is that? Because essentially, I'm giving you, okay, so this is our sort of general reaction here, okay? And we said the general rule was that KEQ, equilibrium constant, K, is going to equal to products over reactants. Now, this product over reactant could be concentration, it could be partial pressure, it could technically be a lot of things, as we can see, depending on the phases. What happens is, that's why we say, product over reactant. I tend to, lean towards concentration of products over concentration of reactants as sort of my general default, because most of the time we get questions that are in solute, in molars, moles per liter. This is usually what we see, concentrations. But in general, what you want to think about is that it's technically some sort of activity of a product over some sort of activity of the reactant. So it could be a concentration as our activity. It could be partial pressure as the activity. In this case, activity of solid or liquid equals, it's always going to equal to 1. So it does not appear in the expression. But the activity of a gas, which is a partial pressure, we get a value for. Activity of a concentration, a solute, aqueous solution, which is a concentration, we get, concentrations, we get square brackets. So I'm going to go through some examples in a second to help you conceptualize that a bit better. Okay, so let's look at this example here. Let's say we have 2A plus B that is in equilibrium with C. Okay, it's a reversible reaction. Great. Let's first pay attention to our phases. So we have a gas phase, we have a solid phase, and we have another gas phase in our product. Okay, so how do we find the KEQ here? So I'm hoping you're pausing the video and trying to do it yourself while I explain right now. So we have KEQ, we said KEQ always equals to something, which activity of product over activity of reactant. So it could be concentration of products over concentration of reactants, or partial pressure of products over partial pressure of reactants. We will determine based on our phases, right? So we also have to note that we have a coefficient here of a 2. Here we have an invisible 1, and here we also have an invisible 1. It's just not written, obviously. Okay. Your teacher or prof, they might not write anything here. They shouldn't. They won't write a 1 here, so you have to clue in that there's an invisible 1 and just always keep track of your coefficients to make sure. Okay, so this is how we would write the K constant, the KEQ. So we have K equals to the partial pressure of C, which is our product, over the partial pressure of A squared. Okay, so we said that if we're in gas phase, it's always going to be partial pressure. So we have that taken care of because these are both in gas, okay? We said if we have a coefficient, it's going to be an exponent. Okay, great. We do not have B here because I said earlier, the activity of a solid or a liquid equals to 1. So it's not included in the equilibrium expression. It's as if there's an imaginary 1 here because all of B we're going to equal to 1. So it's as if we have whatever value you get for the partial pressure of A times 1, which is going to be B because it's solid. So essentially you can sort of pretend that there's no B here, and this is how you write it. Partial pressure of C over partial pressure of A squared. And so we do not include the solid. So that's how you write that. Okay, let's do another example. A plus B is in reversible equilibrium, reversible reaction with 2C. Okay, so we have A, which is in liquid phase, B, which is aqueous phase, and C, which is also aqueous phase. Okay, so try to write your equilibrium expression before I make it pop up. So hopefully this is what you wrote. So we have K equals to the concentration of C, our product, right, squared over concentration of B, our reactant, and there is no A. Once again, A is a liquid. Just like how B was a solid, its activity equals 1. Activity of a liquid also equals 1, so we do not include it. In this case, what are the activities that we're dealing with here? Our activities here were in aqueous phases here, so our activity should be concentrations, which is why we have things written as concentration here. we have square brackets, concentration of products over reactants, and we factored in the fact that we have a coefficient here and we put it up here. So it's always products over reactants, and the activity, aka whether it's partial pressure or concentration, depends on our phases. And remember, we do not include solids or liquids in this expression because it's as if you have an imaginary one or invisible one. They equal to 1 essentially. So this is how we write our KEQ expressions.